Lesson 1.3 covers basic counting principles. In the next few lessons, we're going to cover different counting principles, and this is getting us ready for the topic of probability. Well, just looking over a few concepts of counting theory. In counting theory, an experiment is any process that results in one or more outcomes. You can think of the experiment as the action that's performed. An experiment might consist of one or more actions. If the process is repeated one or more times, each time it's performed is called a trial, and the experiment consists of all the trials. The sample space for an experiment is the set of all possible outcomes for a single trial. Each time I perform that experiment or that action, what are my possible outcomes? That's my sample space. Well, an event is any subset of the sample space. An event can be a single outcome or multiple outcomes, a set of outcomes. And the event is usually the outcome that you want to occur. So for a specific problem, the event is the outcome that we're focusing on. For an example, let's roll a fair die one time. And a fair die just means if you roll it, any side is equally likely to appear up. The experiment, the actual action, is rolling the die. The sample space is my possible outcomes for a single roll. Well, on any single roll, I could roll a 1, 2, 3, 4, 5, or a 6. So those options represent my sample space. Now, possible events, I could consider the event of rolling an even number. What are my chances of rolling an even number? So rolling an even number would be a possible event. Another possible event would be rolling a number greater than 3. I may want to know what are the chances of rolling a number greater than 3. So that's another possible event. Another event would be just rolling the number 2. These are 3 of many possible events. Often if you're playing a game, you set the rules for winning a game. So if 2 children are rolling dice and they say you win if you roll a 6, well, the option of rolling a 6 would be one of our possible events. Now let's look at another example, tossing 2 coins. Well, the experiment, the actual action, is tossing those 2 coins. With the sample space, I'm going to list what could happen each time I toss the 2 coins. Well, first, I could toss tails both times, so I'm just going to write that as TT. The second option, the first coin could be tails and the second coin could be heads. Well, a third option, the first coin could be heads and the second coin could be tails. And then my final option is both coins could be heads. Now let's list some possible events. Well, I may want to know what are my chances of tossing tails on each coin. Or I might want to know what are my chances of tossing the same thing on each coin. That means each coin is tails or each coin is heads. And again, these are just 2 of many possible events that I could have listed. Often we want to know how many possible ways can an event occur. Well, we have several methods for determining the possible number of outcomes in a given situation. The number of outcomes for a certain event is given by the notation N of E, and this is the same notation for our cardinal number, the number of elements in set E. But this time E is the event that we're considering. Often the first step in deciding which method to use is to determine if the experiment is a multi action experiment or a single action experiment? Let's begin by looking at some single action experiments. So if the experiment is a single action experiment, the outcomes for an event are a bit easier to determine because you have fewer possible outcomes. We can often easily just list the possible outcomes, and that's the easiest way to count the total number. So suppose you roll a fair die one time. Find the number of possible outcomes for the following events. So I first want to consider the event of rolling a prime number. Well, what are my prime numbers that I can roll with a single die? Well, if I roll a 2, 3, or a 5, those are prime numbers. So the number of prime numbers is 3. Well, now let's consider the event of rolling an even number. If I roll a die, my possible even numbers are 2, 4, and 6. So the number of ways this event can happen is also 3. The number of even elements when rolling a single die is 3. Well, what about the event of rolling a multiple of a 2 or a multiple of a 3? My multiples of 2 are my even numbers, 2, 4, and 6. The multiples of 3 are 3 and 6. Well, since the 6 is counted in each option, I only want to count it once, don't count it twice. So there's really only 4 ways I can roll a multiple of 2 or a 3. And that's to roll a 2, a 3, a 4, or a 6. Don't count the 6 twice. And then for the final event, rolling a 4 or a 5, how many ways can I roll a 4 or a 5? Well, there are just 2 ways. I roll a 4 or a 5. Now, if I look back at my notation, in the first one I was considering rolling a prime number. So in my parenthesis for my event, I just wrote the word prime. The second example, I wanted to know the number of ways to roll an even number. So inside the parenthesis for the event, I put the word even. The last 2 examples were a bit more wordy. So instead of summarizing that event, I just used the letter capital E to represent my event. And you can put any notation you want to in those parentheses. If possible, I would use words like prime or even. But if it gets too wordy and too long to write, you can just use an E for the set. Now let's look at the last 2 events. In the next to the last example, was it possible to roll a multiple of 2 and a multiple of 3 at the same time? And yes, it was by rolling a 6. Because 6 is a multiple of 2 and 6 is a multiple of 3. Now, was it possible in the last example to roll a 4 or a 5 at the same time? And no, that was not possible. When I roll the die one time, it cannot land on 4 and a 5 at the same time. Well, 2 actions are mutually exclusive if they cannot occur at the same time. We can also say 2 events are mutually exclusive if they have no common outcomes. So the possibility of rolling a 4 and a 5 at the same time are mutually exclusive because they cannot happen at the same time. If 2 events are mutually exclusive, we can use the addition counting principle to find the number of ways these events can occur. With the addition counting principle, you simply add the number of ways each individual event can occur. So look back at the example. You roll a fair die once, find the number of ways to roll a 4 or a 5. Since these outcomes could not happen at the same time, they were mutually exclusive. So I used the addition counting principle. There was 1 way to roll a 4 and 1 way to roll a 5. So I add the 1 and the 1, and that gave me 2 ways to roll a 4 or a 5. Look at the previous example. This was rolling a multiple of a 2 or a multiple of a 3. These outcomes were not mutually exclusive. So I cannot use the addition counting principle in this case. If I added the 3 ways to roll a multiple of a 2 and the 2 ways to roll a multiple of a 3, that would give me 5. And this is the same problem that we had with the Venn diagrams in a previous lesson. There's that overlap of the 6. Since the 6 was counted in each set, it'll have to be subtracted out. And we'll get to this principle later. Look at the next example. You draw a single marble from a jar that contains 12 red marbles, 16 blue marbles, 18 yellow marbles, and 20 white marbles. How many ways can you draw a red marble? Well, since there are 12 red marbles, the number of ways to draw a red marble is 12. How many ways can you draw a red or a blue marble? Well, there's 12 red marbles and 16 blue marbles. If I reach in and draw one marble, it's not possible for that marble to be red and blue. So since these are mutually exclusive, I take the 12 from my red marbles, add that to the 16 from my blue marbles, and that gives me 28. So there's 28 ways to draw a red or a blue marble. In part C, how many ways can you draw a primary color? Well, your primary colors are red, blue, and yellow. These 3 events are mutually exclusive because when I draw one marble, it cannot be red and blue or blue and yellow. It can't be 2 colors at once. So there's 12 red, 16 blue, and 18 yellow. I add these to get 46, so there's 46 ways to draw a primary color. Before we look at the next example, look at the bottom of the page of your notes, and we want to just look at what a standard deck of cards consists of. In any standard deck of cards, there's 52 total cards. Each deck has 4 suits, and the suits are hearts, diamonds, spades, and clubs. There are 2 colors, red and black. Hearts and diamonds are red, spades and clubs are black. There are 13 cards in each suit. You start with an ace, and then you've got the numbers 2 through 10, and then you have a jack, queen, and a king. And there are 12 cards that are considered face cards. The face cards are the jack, queen, and king for each suit. So there's 3 cards in each of the 4 suits, so that gives me the 12 face cards. A lot of the problems in probability use decks of cards. And you're asked, what is the probability of drawing 2 aces? What is the probability of drawing 2 red cards? So if you're not familiar with a deck of cards, you might want to purchase a deck and just look through them, and it'll help you become familiar with them. But for the purposes of this class, the information on this slide is what you need to know about a deck of cards. So now let's look at the example. You draw a card from a standard deck of cards. How many ways can you draw a king or a 7? Well, if I'm drawing a single card, I cannot draw a king and a 7 at the same time. So these are mutually exclusive. There are 4 kings, 1 for each of the 4 suits, and there are 4 7s, 1 for each of the 4 suits. Since they're mutually exclusive, I add them, so there's 8 ways to draw a king or a 7. Now, how many ways can I draw a red card or a spade? Since spades are black, These two sets do not overlap. I can't draw one card and it be red and a spade, so they're mutually exclusive. Well, half of the cards in the deck are red, so half of the 52 or 26 cards are red. Spades are one of my 4 suits, and there's 13 cards in each suit, so there's 13 spades. If I add these, I get 39, so there's 39 ways to draw a red card or a spade. And then finally, how many ways can you draw an ace or a face card? Well, the face cards are just the jacks, the queens, and the kings. They're the cards with the pictures on them of the people with faces. That's why they're called face cards. Well, I can't draw one card and it be an ace and a face card at the same time, so these are mutually exclusive. There are 4 aces, one for each suit, and as we talked about before, there are 12 face cards. I add these to get 16, so there's 16 ways to draw an ace or a face card. Next, let's look at multi-action experiments. A multi-action experiment is an experiment that consists of more than one action. Each event contains one or more possible outcomes for each action. An easy way to visualize this first is by drawing a tree diagram. So let's look at one example with a tree diagram. Let's say you go to a school where the uniform options include 3 colors of shirts, white, blue, and black, and 2 colors of pants, black and tan. Using the uniform clothing, how many different outfits can you make? So we're just going to begin our tree diagram with the 3 shirt options. Since I have 3 shirt options, I'm going to draw 3 branches. The first one is white shirts. The second one is for my blue shirts. And the third branch is for my black shirts. These represent my 3 choices for shirt colors. Then for each shirt that I choose, I've got to choose a pair of pants, and I have 2 choices, black and tan. So if I choose the white shirt, I can have a black pair of pants or a tan pair of pants. If I choose the blue shirt, I can have the black pants or the tan pants. And if I choose the black shirt, I can have a black pair of pants or the tan pants. And for examples like this, you just assume everything matches. So now let's look at our different options. And these are our different outcomes. I could have a white shirt with black pants, a white shirt with tan pants. I could have a blue shirt with black pants or a blue shirt with tan pants. I could have a black shirt with black pants or a black shirt with tan pants. You just follow the branches of your tree to get each outcome. This gives me 6 total outcomes. Another way to obtain the possible outcomes is by creating an organized list. And we're going to do this with the next example. Let's say I roll a fair die and then flip a coin. List the possible outcomes. How many possible outcomes are in the sample space? So first, let's consider rolling the die. I could roll a 1, a 2, a 3, all the way up to a 6. And then when I flip the coin, I could flip heads or tails. So let's start with one option for the roll of the die, which would be rolling a 1. Well, if I roll a 1, that could be followed by tossing heads or tails. So 1H would be rolling a 1 and then tossing heads. 1T would be rolling a 1 and then tossing tails. Now let's go to the next option for the die. I could roll a 2. Well, if I roll a 2, then I could toss heads or tails. So that gives me 2H and 2T. Then continue on for the options for the roll of the die. I could have a 3 followed by heads, and then I could roll a 3 followed by flipping tails. A 4 followed by heads, and a 4 followed by tails. I could roll a 5 followed by heads, and a 5 followed by tails. And then finally, I could roll a 6 followed by heads, and a 6 followed by tails. If I add all of these outcomes, this gives me 12 total outcomes. The tree diagram and the organized list are just good ways to visualize the different outcomes. But sometimes I don't have to list all the different outcomes, especially if I had more than 12 outcomes. So let's look at other ways to find those total outcomes without doing the tree diagram and without doing the list. Let's consider the last two examples. Did the number I roll on the die affect the outcome of flipping the coin? And no, rolling that die and flipping the coin, one doesn't affect the other. If I'm choosing the outfits, did the shirt I choose affect the pants I chose? And that's why I said in these examples, you just consider that everything matches. So picking a certain shirt doesn't limit your choices for pants. So we would say these two actions are independent. Two actions are independent if the outcome of one does not affect the outcome of the other. Two actions are dependent if the outcome of one does affect the outcome of the other. When we're using independent and dependent, these are with multi-action experiments. We have two different actions. We do one thing and then we do the other. And you decide if those two actions are independent or dependent of each other. So let's look at some examples, and I want to determine if these are independent or dependent. So first, I roll a fair die 2 times. Does the number that appears on my first roll affect the number I get on my second roll? And it does not, so these are independent. The next example, I draw 1 marble from a jar, I put it back, and then I draw a second marble from a jar. And we just refer to this as drawing with replacement. When you see the phrase with replacement, that means you put back what you drew the first time. So when I draw from the first jar and I write down what color marble I draw, I put it back. So my second draw, I'm starting completely fresh. I have just the same options that I had with the first draw. So these are independent. But now look at the final example. I draw 1 marble from a jar, I do not replace it, and then I draw a second marble from a jar. This is called drawing without replacement. This time, what I do in my first action, what I do in my first draw, does affect the options I have for my second draw. Suppose the jar only contained 1 blue marble, and I drew it the first draw. Since I don't put it back, for my second draw, I don't have the option of drawing a blue marble. So that first draw affected the outcome of my second draw, so these are dependent. Anytime you draw with replacement, the outcomes are independent. Anytime you draw without replacement, the outcomes are dependent. If two events are independent events, we can use the multiplication principle of counting in order to find the ways those events can occur. This is also referred to as the fundamental counting principle. This counting principle can be used in some situations with dependent events, but you have to be really careful when determining the number of outcomes for the second event. With the multiplication principle of counting, you simply multiply the number of ways each individual event can occur. Let's look at some examples. Think back to the school uniform example. I had 3 options for shirts and 2 options for pants. We did the tree diagram and got 6 possible outcomes. Well, if I multiply the 3 shirts times the 2 options for pants, that gave me the same 6 outcomes. In the next example, we rolled a fair die and then flipped a coin. And that we created an organized list, and that showed us the 12 outcomes. Well, rolling a fair die has 6 outcomes. Flipping a coin has 2 outcomes. They're independent, so I can multiply them, and that gives me the 12 total outcomes. Now for the examples in your notes. At a restaurant, you have 5 salad options, 3 main course options, and 2 dessert options. If a group of 25 people went to that restaurant, is it possible for that many people to each order a different meal? So first I want to find the total number of meals available. And again, for an example like this, you just assume that all the meals go together, that the salad you choose does not affect or restrict the main courses that you choose, and the main courses that you choose do not restrict your dessert options. I have 5 salad options, 3 main course options, and 2 dessert options. If I multiply this, there are 30 possible different meal combinations. So if I have a group of 25 people, yes, all 25 people could order a different meal combination. The next example involves arranging objects. Let's say I have to place 6 books on a shelf. How many different ways can these books be arranged? If I'm doing a lineup or placing objects on a shelf, an easy way to visualize this is I just draw blanks. Each blank represents a spot that a book is going in. And what I'm going to do, I'm going to put my number of choices for each book in that blank. So if I have a stack of 6 books, I have 6 choices for the book that I'm going to put first. So in that first blank, I have a 6. Now for the second spot, I've already placed 1 book on the shelf. So this limits the number of books I have to choose from for my second spot. So I only have 5 books remaining in the pile. So I have 5 choices for the second book on my shelf. Now for the third spot, I've already placed 2 books on the shelf, so I just have 4 remaining to choose from in my pile. So I have 4 choices. And this pattern continues. Now that I've placed 3 books on the shelf, I have 3 left in my pile to choose from. Then for the next book, I only have 2 left to choose from. And then finally, for the last spot on the shelf, there's only 1 remaining book. Now, each time I placed a book, I was limited to the number of books left to choose from, but I could choose any of those remaining books for the next slot. So I'm still going to use the multiplication principle, and I'm going to multiply these. If I multiply these, that gives me 720 possible arrangements for those 6 books. In the next example, how many different 6-digit license plates can be made if the first 3 places are letters and the last 3 places are digits? So the license plate has 6 positions on it. So I'm going to draw 6 blanks. The first 3 blanks have to be letters. there are 26 possible letters. So in that first position, I could use any of the 26 letters. For the second letter, I wasn't given any restrictions. Like I wasn't told that letters can't repeat, or I can't use a vowel, or I can't use the letter Q. So for my second letter, I still have 26 options. Same for my third. For my third letter, I have 26 options. Now the last three positions have to be digits. There are 10 total digits. I've got the numbers 0 through 9. So for my first digit, I have 10 options. I can pick a 0, a 1, or 2, all the way up to a 9. Like the letters, I wasn't given any restrictions. So for my second digit, I still have 10 options, and the same 10 options are available for my third digit. Now the letter I pick for the first digit doesn't affect the letter I pick for my second digit, so these are independent. I can apply the multiplication principle and multiply these. When I multiply this gives me 17,576,000 different possible license plate combinations. Now our next example is similar to the previous one, but I do have some restrictions. How many different 6-digit license plates can be made if the first 3 places are letters and the last 3 places are digits? But this time, no letter or digit can appear more than once. So we'll draw our 6 blanks. For the first letter, I have all 26 letters of the alphabet to choose from. For my second letter, I have the 26 letters of the alphabet, but I can't use the same letter that I just used. So I only have 25 left to choose from. For my third letter, I can't use any of the previous 2 letters. So I have 24 letters left to choose from. Now the last 3 positions are digits. So for my first position for the digits, I have all 10 digits to choose from. For my second position, I can't use the digit that I just used, so I only have 9 left to choose from. And then for the last digit, I can't use the previous 2 digits, so I just have 8. I can apply the multiplication principle, and this time there are 11,232,000 different possible license plates. Let's look at the next example. How many ways can 5 men and 5 women be placed in a line if all the women line up first? So I've got 10 total people that I'm lining up. So I'm going to draw 10 blanks. The first 5 blanks represent women. I put the women first. So I have 5 women to choose from. This one is similar to arranging the books on the shelf. So for my first position in line, I have 5 women to choose from. Now once I place a woman in line, I only have 4 left to choose from for the second position. Now I have 2 people in line, so that only leaves me 3 women left to put in the third position. Now I have 3 women in line, so that leaves me 2 left for the next position. Now I have 4 women in line, so that just leaves me 1 choice left for that last position for the women. Now the last 5 positions are the men. So I start out with all 5 men to choose from. Once I place 1 man in line, I have 4 choices for the next position. Now that I've used 2 men, that leaves me with 3 men for the next position. And then likewise, I have 2 men left, and then 1 choice left for the final position. If I multiply these, that gives me 14,400 different possible lineups for putting the women first, followed by the men. Next, let's look at how many different ways can 5 men and 5 women be placed in a line if I alternate the men and the women, and either a man or a woman can be placed first. So let's draw the 10 blanks. My first position can either be a man or a woman, so I have 10 total people to choose from. Now let's consider the second position. It's either going to be a man or a woman. I don't know who I put first. I don't know if I put a man or a woman first. But for my second position, it's going to be someone of the opposite gender. And I haven't used that gender, so I have all 5 options left. Now in my line, I have 1 man and 1 woman. I don't know what order, but I have 1 of each gender. So for my next 2 positions, I'm going to put a man and a woman. And since I've used 1 of each, I have 4 of each left. So now in my line, I have 2 men and 2 women, and they're alternating. That leaves me 3 of each gender left to choose from for the next 2 positions. Now in my line, I have 3 men and 3 women, so that leaves me 2 of each gender to choose for the next 2 positions. And for the final 2 slots in my line, I only have 1 man and 1 woman left to choose from, so I only have 1 choice for each slot. When I multiply these, I get 28,800 different lineups if they alternate and either a man or a woman can come first. Now for the final example, how many different 4-letter codes can be formed using the letters A, B, C, D, E, F, G, H, I, J, K, and L? So it's a 4-letter code, so I'm going to draw 4 blanks. I can't use all the letters in the alphabet. I can only use the letters that I have listed. Since I'm given specific letters, I'm going to assume that no letter can be used more than once. On a test or a quiz, I'll try to be more specific to let you know if the letters can be used more than once. So of the letters listed, I have 12 possible choices. So the first letter in my code, I have 12 options. Once I use a letter for that first position, that only leaves me 11 remaining letters for the second position. So for the second letter in my code, I only have 11 options. Now I've used 2 letters of my 12 total. So for the third position in my code, I have 10 options. And then for the final position of the code, I've used 3 of the 12 numbers, so that leaves me 9 remaining options. If I apply the multiplication principle and multiply these, I'm given 11,880 different code combinations.